Hello, my name is Ritik Dutta. I'm a PhD student at the Peace Lab ASU. Today I'm going to talk about my project. The title of this project is Low Cost Hybrid Silicon Carbide GaN-based single stage microinverter with leakage integrated planar magnetics technology. This project is sponsored by the Department of Energy. Basically, this project has two parts, and I'm taking care of one part. The project lead is Dr. Ann Malik, and I'm working under his supervision on this project. In the conventional DC to AC inverter, a DC link capacitor is used in the DC side. So the DC link capacitor that is used here is bulky and less reliable. This is used to mitigate the double line frequency ripple, and our objective in this work is to replace this DC-link capacitor with an active power pulsating buffer, which would make the system more compact and also enhance the reliability of the system overall. So the microinverter parameters are: the power is 500 volt amperes, the input voltage is 25 to 40 volts, the line frequency is 60 Hz, and the maximum allowed ripple is 4 volts. So for this configuration, the DC link capacitor in the traditional manner needed will be 8.3 millifarad. So that capacitor will require a large space, so it would take a large volume, and also it would lower the reliability of the whole system. As the capacitance is high, so we cannot use the ceramic capacitors or the film capacitors in the DC link capacitor. So we have to use the aluminum electrolytic capacitors here. So those capacitors are less reliable than the format 2. So our objective of this work is to replace the bulky unreliable DC link capacitors with the active power pulsating buffer. So our workflow will be the formulation of the loss model. We will try to minimize the loss and the volume. So for that we will have to formulate the loss model, and then we'll have to design a feed forward controller so that the active device will be stable. And for minimizing the both the loss and the volume, we'll have to optimize the inductance and the capacitance. Therefore we will be able to reduce the volume of the system and also enhance the reliability of the whole system. Here we can see the whole schematic where the bulk power pulsating buffer is connected to the output of the solar array, and which is also connected to the input of the bridge driver. So instead of the DC link capacitor, we are using this active power pulsating buffer. So for low voltage applications, generally buck or boost derived power pulsating buffer is used. So we are using the buck-derived PPB as the voltage stress across the devices or the capacitor is less here, and also the inductance required is also less here. So there will be more flexibility in selection of power semiconductor devices and capacitors. Also, it will have a lower volume than boost or other PPB options, but it has certain drawbacks. So it will require more capacitance than the boost option, and also the loss incurred in the buck power pulsating buffer will be more than the boost or the or any other PPB topologies. Formulate the loss model, we need the high frequency and low frequency current component of the power pulsating buffer circuit. So we calculated the high frequency current component through Fourier analysis, and we got the low frequency current component from the analytical equations. As mentioned earlier, we used feedback control system in our circuit. So there are two loops in this system. The first loop is the outer voltage control loop, in which the capacitor voltage Vc is regulated as per the reference voltage Vref to govern the power flow through the capacitor. The second loop is the inner current control loop, which is there to regulate the inductor current Ic as per the reference current Iref to govern the overall PPB power flow. And the feed forward control loop is also seen, where we can see the inverter current is controlling the feed forward control loop. An optimization procedure is run to select the power device, capacitor, inductor, and the switching frequency. so that we can minimize the total loss and the total volume of the system. From the eta Pareto optimization result, we got our design, the selected capacitor and the inductor. So we got our required capacitance as 1.9 millifarad and our required inductance was 19.5 microhenry. So we can see previously the required capacitance was 8.3 millifarad, and now with our design the required capacitance became 1.9 millifarad. So the required capacitance reduced by almost 77%. Different power devices, capacitors and inductor cores are considered for using in the power pulsating buffer circuit. So the optimum one with the lower loss and lower volume are selected here. So for the power device we used EPC 2218. For the capacitor we used a 22 microfarad ceramic capacitor, and for the inductor we used 0077930A7 inductor core. Here we can see different optimization results. So from the first figure, we can notice that the losses are the least at 100 kilohertz frequency. In the second figure, we can see that with the power level, the efficiency is also increasing. In the third figure, there is a loss breakdown for different components of the power pulsating buffer circuit. In the fourth figure, it is shown that the voltage ripple is always less than 10% ripple, no matter what the DC link voltage or the power is. Here the selected components are shown, the power devices, inductor cores, the turns, capacitors, and the switching frequency, heatsink, and the total volume is also mentioned here. So in the right, the PCB of the power pulsating buffer is shown. So in the top we can see the capacitors, the inductor, and the power devices are situated, and in the bottom side there is a voltage and a current sensor situated. This is the whole microinverter circuit. So different components of the microinverter circuit are shown here, and the left figure is the design power pulsating buffer, where the ceramic capacitors, the inductor, and the heatsink and the uh, power devices are shown here. So as we can see from the figure, it is only 57 times 40 millimeter. So we can have a volume reduction around 51.36% if we use this power pulsating buffer instead of the DC link caps. So this is the microinverter circuit, where this is the input side and this is the output side. This is the power pulsating buffer circuit, which is connected to the input side of the microinverter. Here an electrolytic capacitor is kept to show the comparison among these, and the ceramic capacitors in the power pulsating buffer and the inductor is connected in series, while there are around 90 ceramic capacitors stacked in parallel. So there is a half bridge under the inductor, which can be seen from here. So this device is quite smaller compared to the electrolytic capacitor banks. As you can see, there are three spaces available for the electrolytic capacitors, and this PPB is consuming less space than those. So it is almost saving 50% of the space here. And also, as we are not using the electrolytic caps here, so it is also enhancing the reliability of the whole system. So these two results compare the system before and after, including the power pulsating buffer in the system. So the left figure, or the A figure, is with three electrolytic caps, where the DC link voltage ripple is 4.1 volt, which is almost 10% of the input voltage. And in the right one, we can see the DC link voltage ripple became 3.9 volts, and also the voltage profile has improved, and so it will have less THD and will have a better signal characteristics. Here, a comparison among electrolytic solution, boost design presented in number 1 reference, buck design for a high power system presented in number 2 reference, and our proposed buck design is presented. So from this comparison chart, we can see the volume has reduced 51.36% and the capacitance has reduced 77% compared to the electrolytic solution, and the volume is much less than the boost solution. So from the volume perspective, the buck design is much more appropriate than the boost design, although the buck design has slightly more loss than the boost design or the electrolytic solution. So in order to minimize the loss and further minimizing the volume, in the future we are planning to introduce the CRM operation instead of the CCM operation to reduce the whole inductance and the loss, and also we will introduce the interleaf structure to reduce the losses across the device. So thank you very much for staying with me. If you have any question or doubt regarding this project, you can reach to me via my email. So I'll be very much glad if you do so. Thank you.